Okay, in this tutorial we're looking at section 5.6, which is applications of trigonometric functions. Okay, so we've got no real new theory to go through here, we just have a worked example that we can look at. Okay, as per usual, our worked examples, our application questions are quite important. We've got to have a good understanding of them. So you need to make sure that you get through this work and that you really have a firm understanding of this for your SACs and exams. So we've got one worked example that we can have a look at. So we have the circle shown has a radius of 1 unit, so if you like it's a unit circle. Okay, and we've got a point here, so that should be our origin as well. And then we've got the points Q over here, R and P. Okay, and R set up so that it's at right angles to Q. Okay, so we end up with two right angles triangles, and we also have theta in there, our angle. Okay, and we need to show that the triangle, so our triangle OQP, so O, Q and P, so this big triangle, has an area A equals a half cos theta. Okay, where our angle in here, QO and our X, okay, is theta, okay, and it's measured in radians. Okay, and then we'll get to part B in a second. So we know as RQ is parallel, so this line here is parallel to our x-axis, okay, then we know that we can say that our angle RQO equals theta. So RQO, this angle in there, okay, is also going to equal theta. Okay, that's from our parallel line work, okay, from year 10. Okay, and that's basically because it's an alternate angle, if you remember the terminology. Okay, so that means that cos of theta, okay, is going to equal our RQ, okay, over our OQ. So just because cos is adjacent over hypotenuse, so it's going to be the line RQ over OQ. Right? And we know that O to Q is equal to 1 because our radius is 1. So we know that cos of theta is equal to RQ on 1. Okay. And so we also know that our line O to P is equal to 1 unit as well. Okay, so we know then that cos of theta equals RQ. Right, we know the length of the line OQ and OP equal 1 unit in length. Okay, so our area, I'll do it up here, our area equals a half, okay, times our base, which is OP, times our height, which is RQ. Okay, and now we know OP equals 1, so we have a half times our length of OP, which is 1, times RQ. Now we just said a minute ago that RQ is equal to cos theta. So that our area is equal to a half cos theta as required. Okay, so we want to find, so we're saying that's A for our area, so we want to find in part B dA d theta. So the rate at which the area is changing with respect to theta when theta equals pi on 6. Okay, so we know that our A equals a half cos theta, so dA d theta. Okay, cos goes to minus sine or negative sine, so it becomes negative a half sine theta. Okay, when we put in our theta equals pi on 6, okay, then dA d theta becomes negative a half sine of pi on 6. Okay, and we should be getting pretty good at knowing our exact values by now. We know that sine of pi on 6 is also equal to a half. Okay, if you're still having trouble remembering our exact values for our trig functions, you need to get your head around that, you need to practice them. Which means we get negative half times a half gives us a quarter. Okay, so the rate at which the area is changing with respect to the angle is a negative a quarter units. Okay, we don't have any units of measurement, so we just call it units. Okay, so there's not too much else in this section. Okay, so we can have a look at one more worked example though, but it's along similar lines. Okay, to ones that we've seen in the past. So what we're looking at, okay, is worked example 12 this time. Okay, and we're saying the temperature on a particular day can be modeled by the function temperature T of T equals negative 3 cos of pi T on 9, okay, plus 18, okay, where 0 is less than or equal to T less than or equal to 18, okay, where T is in T is in hours. T in hours after 5 AM, and T is temperature in is our temperature in degrees Celsius. Okay. For the remaining 6 hours of the 24-hour period, the temperature remains constant. Okay, we want to calculate the temperature at 8 AM. Okay, well we need to think T is our time in hours after 5 AM, so 8 AM is going to happen when T is 3. So for the first part, we're just saying T of 3 equals negative 3 cos of pi times 3 on 9 plus 18, so we get negative 3 cos of pi on 3 plus 18. Okay, as I said a minute ago, we need to be starting to get good at our exact values. Okay, cos of pi on 3 is equal to a half, so that negative 3 times a half plus 18. Okay, which means we get minus 1.5 plus 18, which gives us our 16.5 degrees Celsius. Okay, so that's part A for this worked example. Part B is, at what times of the day is the temperature 20 degrees Celsius? Give your answer correct to the nearest minute. Okay, so this time we're setting the temperature equal to 20. Okay, so we're saying, well, 20 equals minus 3 cos of our pi T on 9 plus 18. Okay, and we've got to solve it for T. Okay, so what we do is we take away our 18 and make it 2 equals minus 3 cos of pi T on 9. We could divide by our minus 3 and say we've got minus 2 on 3 equals our cos of pi T on 9. Now the problem is minus 2 on 3 isn't one of our exact values. Okay, which means we can't do it by hand, which means simply we can ask our calculator to solve that. Okay, and you can set your domain from 0 to 18 when you're solving that. Okay, so we end up getting T equals 6.6 and 11.4 when we do that. Okay, so T being 6.6, that equates to 11:36 AM, and our 11.4 corresponds to 4:24 PM. Okay, so you just have to do a little bit of work there. Okay, so the temperature is 20 degrees at these two times. Okay, for part C, okay, we've got to find dt. Okay, so looking at this, okay, because it's cos, it's going to go to negative sign. Okay, we've got a constant of pi on 9 inside, that's got to come out the front. So we're going to have our double negative, because cos goes to negative sign, so they're going to cancel each other out. So we'll have 3 times pi on 9 sine of pi t on 9. Okay, and our constant's going to disappear. Okay, which means we're going to get it as pi on 3 sine of pi t on 9. Okay, and yeah, so that's all we're going to do for that part. Okay, and part D, right, is at what rate of change of temperature at the times found in part B corrected 2 decimal places. So what we're saying is we want the rate of change in temperature at our 2 times that we found earlier, at these 2 times. So we need to go dt equals our pi on 3 sine of pi on 9 times our 6.6. Okay, we need to use our value there for t that we had. When we get that it is 0.78 okay, degrees per hour. Okay, our other one is our dt equals pi on 3 sine of pi on 9 times our 11.4. When we do that, and for both these, don't think that you need to do them by hand. They're absolutely just put them in your calculator. That gives you negative 0.78 degrees per hour. Okay, so you should notice from the last couple of worked examples and some of the other application stuff that, well, part A and B was what we've already done in application questions for trig functions. We've already seen questions like this. They aren't new. We've seen them when we've done our trig. Okay, so the first 2 parts is just utilising those skills that we've used before. Then we're chucking in a rate of change part, which is needing to use our new work on derivatives. Okay, so hopefully that's enough to get you through the questions. Again, very, very important that you get your head around these questions, that you do as many as you need to make sure you have a really good understanding of how these work.